Yes?
Yes, we are now able to see the screen.
All right. So what we were talking about, sorry for that, because there's a problem with the internet, I think, wherever I am. So what we were looking at last time is the Simpson's rule, and which is the same as that is Simpson's 1/3 rule, which is the same as Newton-Cotes formula for n is equals to 3. Then we were talking about taking a curve which passes through the set of values x naught, y naught, up to xn, yn. And this should be a polynomial of degree 3. So suppose we have the function f of x. So we have it for x is equals to a, and we have x is equals to a plus 3h and so on, up to x is equals to a plus nh. Sorry, we were supposed to look at, actually we were supposed to start from Simpson's rule, or 1/3 rule, which is the Newton-Cotes formula for n is equals to 2. Sorry, n is equals to 3 is what we are supposed to be doing today, but this is what I wanted to review again. So we have this function y is equals to f of x. Then we have for the values x is equals to a, x is equals to a plus 2h and so on. Then this is passing through the points which represent a parabola. Then we have the i's, I1, I2, I3 up to In. We made up to that point, so we are supposed to evaluate this integral, the first integral, that is the I1, I2, I3, and so on. Then we sum them up so that then we are able to find the value, the numerical value of that integral. So that is what we have. We have those values. If we take x to be a plus rh, then the x to be equal to that. then we have the limits now. We'll have to change from x is equals to a, and then that's for r is equals to 0, then x is equals to a plus 2h for r is equals to 2. So that's what we have. And when we expand this now for f of a plus rh, we'll get to these integrals that we have here. Now, because the curve is passing through the points x0, x1, and so on, and this is a polynomial of degree 2, then the differences of order higher than 2 will, of course, vanish, so that we have the following. This is what we have for the first evaluation of the integral. We'll get to h over 3 y0 plus 4y1 plus y2 when you evaluate that integral. Then in the same way, when you work out, this is I think where we stopped last time, when you work out the second integral, you will get what we have there. And in the same way, if you evaluate the third integral, you will get h over 3, then y4, 4y5, y6, so that if you continued in that order, if you go to say I4, this will be h over 3, then we have y6 plus 4y7 plus y8, and so on, up to in, which gives us that. So if we add up all these, the I1, I2, I3, and so on, then we expect to get what we have here. So then this will be h over 3, y0 plus yn, then there is 4 times y1, y3, up to yn minus 1, then twice y2, y4, y6, and so on. So this will be known as the Simpson's 1/3 rule, where we have come up with this one from the following. This is what we had, is that this is our y1, sorry, our I1. This is what we have. So we have h over 3, y0 plus 4y1 plus y2. So for I2, we have h over 3, y2 plus 4y3 plus 4y4. So you look at this for y0, and the yn, of course, sorry, the in, we are going to have yn. Is that one there? This will just be h over 3 y0 plus h over 3 yn. That's the first one. Then now there is going to be for y1, there is 4y1, there is 4y3, there is 4y5. So then there is plus 4 times, we start y1. Of course, there is, if we can factor out h over 3, because in all the situations, there is going to be h over 3. Then there is y0 plus yn. Then for the 4 times, there is this 4 times y1, 4 times y3. So this y1 plus y3 plus y5 plus, and so on. Then again, when we come to y2, you see this is h over 3 y2. Then there is also a h over 3 y2 here for I2. Then again, there is h over 3. Okay, now this one goes to y4. So if you go to the fourth I, there is going to be another y4. So for the y2, here we have h over 3 y2. Then there is another h over 3 y2 here. So this and that will be twice h over 3 y2. That is why we have plus twice y2, and then plus y4 plus, and so on. And that is what we have here, that there is going to be h over 3 here. Then there is y naught plus yn. There is y1, y3 up to yn minus 1. Then twice y2, y4 up to yn minus 2. So this is the Simpson's one-third rule, or Newton-Cortez formula for n is equals to 2. So when applying this equation here, one thing that you're supposed to note is that the given integral should be divided into an even number of equal subintervals. Otherwise, it will not be applicable. Then now, we look at another formula altogether today, and this is what we call the Newton-Cortez formula for n is equals to 3. So for this case, we consider a curve which is passing through the set of values x naught, y naught, up to xn, yn, and this to be considered as a polynomial of degree 3, so that the differences of order which are higher than 3 will vanish. If we have this function f of x be tabulated at these particular points, so for this case, we have x is equals to a, we have x is equals to a plus nh, respectively, then obviously we're going to have something like this. We will have our integral will be equal to, we'll have this going to, we have the integral from a to b, and this will be equal to, we have a to a plus 3h fx dx plus the integral a plus 3h, a plus 6h, of course, fx with respect to x, plus all the way the integral a plus n let's call that equation 1. So then we can have for I1, obviously, this is going to be our first I, and that is going to be the second one. Of course, that's going to be 3h f of x dx. And of course, this is going to be uh, 0 to 3 h. That is, if we have it that x is equal to a plus rh, that's our x. And then, of course, from which we can find the x to be h times dr. That is how, once we make this substitution, that is how the f of x changes to f of a plus rh. Then now we differentiate, we integrate with respect to r. Then the limits of integration, of course, will change to from 0 to 3. So the limits are 0 and 3. Of course, for x is equals to a, and x is equals to a plus 3h. So So this particular, once we have that, then we expand this to get that polynomial using so it gives us this for our I1. So this will be h, and this integral is 0 to 3. Doing that with respect to R, when we work differences of order higher than 3, because we took a polynomial of degree 3. So we'll have to neglect that. And then we will get to this I1 will then y0 plus 3y1 plus 3y2 and plus y3. And in the same way, we can be able to work out I2, and I2 will then take this form. I2 will be 3h over 8. You can verify that. And y3 plus 3y4 and so on. I3 is equal to that, and so on, up to in. Now, of course, we can add up all of them, because what we're interested in is the I, which is the sum of I1, I2 up to in. And this gives us this 3h over 8. Again, we have the first and the last, y0 plus yn. And we have 3 times the y1, y2, y4, y5 up to that. Note this one here. We have yn minus 2 plus yn minus 1. Then we have twice y3, y6, and so on. And what we have here is what is referred to as the Simpson's rule, Simpson's 3 over 8 rule, or what is called the Newton's Cotes formula for n is equals to 3. So we have for n is equals to 1, for n is equals to 2, and n is equals to 3. And that is what we have for that case. Any questions up to that point? Any questions up to that point?
The only concern is that you are a little faster today, flipping from one page to another.
Yes? What? What's the question again? So we can then proceed and see what happens in the case when n.
Excuse me.
Yes?
Please go back to the previous page.
I'm not getting it. Yes?
Sir, could you please go back to the previous page
Could you share
for a
the
second?
This is where we are. Yes, there we are.
Just scroll down a little.
What do you mean scrolling down? Another page back? You know, down a little bit means we go back to,
Yes, please.
we go to where we are now.
Go back to the previous one at the start of the Newton-Cotes formula for n is equals to 3.
Yes? That's what you mean? So we have the i's, we have those, the integrals, the I1, I2 up to IN. For us to work out IN, the limits will change from 0 to 3 because of these substitutions here. Yes? So this is what in the next slide, this is what we are going to expand. When we expand this.
Excuse me, sir.
Yes?
Please go back to the previous one before this one at the start of the Newton-Cotes formula for n is equals to 3.
Yes? That's the starting point. Where in this case now, after getting these tabular points, we will then talk about the integral. This will be a to b of fx dx, which will be the same as a to a plus 3h f of x dx plus a plus 3h a plus 6h f of x dx plus and so on. Is that okay?
Yes, yes.
So let's look at a case where now we are considering a case where n is equals to 4. So if we take n is equals to 4 in the general formula, then we neglect all the differences above the fourth order, then we will get the following. We get the integral 0 to x naught plus 4h of f of x with respect to x. And this will be given by 4h y naught plus, you can verify this again when you build up the forward difference table to get to the polynomial. So when you evaluate that, you get 2h or 45, 7y naught, 32y1 plus 12y2, 32y3 plus 7y4. Similarly, so I'm saying we take n is equals to 4 in the general formula, which we have had a look at before more than once. And then now, in this case, we neglect all the differences above the fourth order, because in this case, we are taking n to be equal to 4. So in the same way, for what we have here is our first, this is like our I1. It's like our I1 now in that case. Then we can proceed in the same way. We get now the integral x naught plus 4h. Then here we have x naught plus 8h. Again, this will be equal to 2h, 45, 7y4, y5 plus 12 y6, y7 plus 7 y8. Which shows you if this be the same procedure, then we can also have this is like our I2. Then we can have our I3, which will be the integral. We have x naught plus 8h, then x naught plus 12h of our fx dx. So this will be 2h or 45. Again, this will be 7 y8 plus 32 y9 plus 12 y10 plus 32, then plus 7 y12, and so on. And so on, so that we get to our nth value, so that adding if we add all those integrals from x naught to x naught plus nh, we will then get the following. We have the integral from x naught to x naught plus nh of this function f of x with respect to x. So this will be 2h over 45. Then we have 7 y naught plus 32 y1 plus y3 plus y5 plus and so on. Then plus 12 times y2 plus y6 plus y10 and so on. Then plus 14 y4 plus y8 and so on. And this is known as the Ball's or the Newton-Cotes formula for n is equals to 4. So Newton-Cotes formula for n is equals to 4. One thing that you're supposed to observe in this case is that while applying this Ball's rule, the number of sub-intervals should be taken as a multiple of 4. In the application of Paul's rule, the number of sub-intervals should be taken as multiples of 4. So that is one thing that you're supposed to note, that while applying this Paul's rule, or the Newton's formula for n is equals to 4, make sure the sub-intervals are taken as multiples of 4. That is the only way that you can be able to apply that formula effectively. So maybe we can have a look at an example here.
Please go back to the previous slide. There is something I did not see.
All right. That one? Is that the one?
Okay, it's okay.
Excuse me.
Yes, please.
I do have a question on the n power 3.
Yes.
The n is equals to 3 for Cortez formula.
Yes. What about it?
In the instance, say you have the number, the y is going up to say an 11th term. The last bracketed items had mentioned yn minus 3, and from what I've seen, like they do have a similarity in the differences. Say for example, like I3 has y6. No, wait.
You see, one thing that you are supposed to note very fast before you think how far the differences will go is actually this first statement, for example. But in this case, we are thinking of a polynomial of degree 3. For n is equals to 3, we are thinking of a polynomial of degree 3. So that when you are working out your i's, the I1, I2, I3, and so on, you remember that what we are working on is a polynomial of degree 3, so that any other differences which are higher than order 3, they will vanish. They will go to 0. So that when you work out your difference table, it will reach a point where you have 0, 0, 0, 0 up to the end. So that is one thing that you are supposed to note as you start employing any formula that you are given, or how far you are going to go. You will go with the differences. Have I answered your question?
Partly.
What did you think yourself?
Because I'm seeing there's a common trend in how the y's are being placed. Like if in the event there's a discrepancy.
That is true, because like you saw, when we were looking at the Ball's formula, I've talked about from the general formula. That means when we start n is equals to 0, trapezoidal rule, n is equals to 1, and so on, we have generalized. In fact, there is even a case where n is equals to 5. So the trend is the same, but now you're supposed to be wary about how far are we going to this polynomial. where are we going to stop with the difference in the difference table to pull out the values, fix them into the formula, then work out what we require, right?
Yes.
Okay.
Thank you.
So let's look at number here. I think I'll just do one formula. Evaluate 0 to 1. Using Simpson's by dividing equal parts. These are equal parts. Also, so this using Simpson's 1/3 rule, and then 3/8 so now dividing 0, 1 into 4 equal parts, having the interval length will be 1/4 or 0.25. So we have the following then. We have for the starting point, x naught will be 0. So we have y naught will be equal to 1. Will be 1/4. Then if x1 is 1/4, then y1 will be 1/1 plus 1/16, which will be 16/17, 0.9412. When x2, 1/4 plus 1/4 will be 1/2. So we have y2 will be 1 plus 1/4, which is 4/5, that is 0.8. Then we have x3, 3/4. So y3 will be 1/1 plus 9/16. And this will be 0.64. And then finally, x4 will be 1. And therefore, y4 will be 1 plus 1, which is equals to 0.5. So notice that when we are getting to the y values, once we subdivide the given interval, like in this case for 4 equal parts, then it means that for us to get to the y values, we go back to the integrand, and the integrand in this case was, we were working on the integral from 0 to 1 dx, 1 plus x squared. So that is what we have. So for this first case, if x naught is equals to 0, then our y naught is going to be 1/1 plus 0 squared, which gives us 1. Then for x1, which is 1/4, then this will be 1/1 plus 1/4 squared, which is 1/16. And that's why we get to those figures as what we have there. So we have the y's, we have the x's, then now we employ the formula. So by Simpson's 1/3 rule, we have the integral from 0 to 1, y. This will be equal to h/3. We have y naught plus yn plus 4 times y1 plus y3 up to yn minus 1 plus twice y2 plus y4 plus yn minus 2. That's what we have for Newton's 1/3 rule. So this will be h is the step length, which is 1/4. So this will be 1/4 divided by 3. Then we have y naught plus yn, so that will be 1 plus 0.5 plus 4 times y1, 0.9412 plus y3, which is 0.64. There is this y2, which is 0.8. And when you work out this, you get 0.7854. Any questions on that before we apply the 3/8 rule?
Please go back to the example, to the start of the question.
Said I go back to the start of the question. This is where we are. That's where we are. So we have to evaluate that, or we estimate the value of that integral using Simpson's third rule. And then we are required to divide the interval into 4 equal parts. Then we are supposed to use 3/8 rule. So what is the question again? Yes?
Can I ask that is the 3/8 rule the same as the 1/3 rule? That is the other name, the Simpsons that rule.
No, 1/8, 1/8. Are you sure it's the 1/8 rule is the same as 1/3?
No, I was asking a question.
Did I use 1/8 when I was deriving it? Yes? Are you getting what I'm saying?
No?
Yes? So what is the 3/8, the 3/8 rule? What is the formula like? So we have the y's, we have the y naught up to y4, then we have the x. Now let's see what happens with the 3/8 rule. We have that integral will be 3h over 8. We have y naught plus yn now plus 3 times y1 plus yn minus 2 yn minus 1, then plus twice y3, y6, and so on, yn minus 3. So how is this one going to be? We have y naught. What is going to be our y naught? 1, and yn is a half plus 3 times y1 is 0.9412, sorry, plus y2 0.8, yn, that's y4, n is y4, yn is 4. Again, we go back to y2. Is it? So it stops at that point. This goes up to that point, right? Then plus twice y3 is 0.64. Then we don't have y6. So this will be, what's the value of this? 3/4 into 3/2 plus 3 times. You can find the value of that plus 0.8, then plus twice 0.64. So you can be able to find the value of that. If we were to use the 3/8 rule for that question. You can also try the following. Any questions? Is there any question on the example that we have just done? Yes. Yes. I didn't get the question. We used the same interval for the same question. Otherwise, if we were given an alternative about the intervals, we were told to divide the 0, 1 into 4 equal parts in both cases, and working out their third rule and the 3/8 rule. Yep. So let's try the following. The first question is compute the value of the integral. We have yx dx, which is equals to the integral from 0.2 to 1.4 sin x minus the logarithm of x using one trapezoidal, two Simpsons, and three the Simpsons 3/8 rule, and then false. Divide the given interval into 12 equal parts with the step length as 0.1. So, of course, in this case, once you get a question like this, and then you have the exponential and trigonometric functions, you will have to convert your calculator to work it out in not in degrees, but in radians. Work it out in radians. And of course, in this case, then we will have, what you will have is that your x naught will be, of course, 0.2. Then, of course, x1 will be 0.3, x2 will be 0.4, and so on. So that you have your x12 will be what we have as 1.4 there, 1.4. So when working out now your y naught, y naught will be sine 0.2 minus the log base e over 0.2 plus exponential 0.2. Like, can somebody work for us that one? If you change your calculator to be in radians, what is going to be the value of that? Can somebody work it out for us? I don't have a calculator myself here now. Somebody to work out that for us?
It's 0.1105.
0? Are you working on with radians?
Yes, with radians, I have 0.1105.
What about degrees?
With radians, I have 3.0295.
With radians, actually it's 3.0295. It's 3.0295. You should note that very carefully, otherwise you will be working out, this should be 3.0295. This is the correct figure. So the same way, you can then work out your y and so on. Then now working out, since you have all the formulae, you can do the substitutions and work out the approximate value of that given integral. Let's look at the
Excuse me,
second
sir.
question here. Yes.
Do we need to know how to derive these formulas, like the trapezoidal, the Simpson's third rule, and the Simpson 3/8, and the Boyle's rule?
Yes.
Do we need to know how to derive these formulas?
It's good for you to understand how it gets there, you know, and the only way that you can understand how it gets there is to understand how you derive it. But obviously, I will not ask you. I can easily ask you to derive it because now that I'm aware you are going to do your exams in college. So you must understand how you reach that point. So let's see the second question.
Excuse me, please go back to the first question.
What is it that you want there? I will. Let me first write this. Discharging so we have the height in meters, the area in square meters, 10, 14, 950, now if minutes. A, estimate yes, water level to fall from 14 meters to 10 meters. So a reservoir is discharging water through sluices at the depth H below the water surface area A for various values. H is given below. So we have the height in meters, then the area in square meters. So you have that table there, which goes from 10, H goes from 10 to 14, and the area goes from 950 square meters to 1530 square meters. So if we have T denoting the time in minutes, the rate of fall of the surface is given by that formula. This is what we have. So I think I need different color. This is the formula that we have.
Excuse me.
The question is, yes?
The lower part of the formula is not visible.
Are you able to see, estimate the time taken?
No, I'm only able to see estimate the, below that I'm not able to see.
So what, you can't see that? Right? Up to there, isn't it? So the question is, so the question was, estimate the time So that is the question now. You're supposed to estimate the time taken for the water level to fall from 14 meters to 10 meters above the sluices. So in this case, what you're supposed to note is that what is expected of you is you will have to find that integral from A to B with respect to x, which is the integral from 10 to 14 of A with respect to H. Of course, you have the y values, you have the y naught, y1, y naught is 950, all the way to y3 or y5 is the last figure. And so on. Anyway, this is what's expected of you for that case. You have the x values, and then you have the y values as given in the table. then you're supposed to work out this. I expect you to get the question again, the time taken for the water level to fall, that expect it to be 25.27 seconds. So what's I expect you to get. Then I have another question here. Of, the x-axis. The curve. The coordinates. So we have x and y, 0, 0.25, 0.5, 0.75, and 1.0. This is 1.96, 0.89, 0.8415. A solid of revolution is formed by rotating about the x-axis, the area between the axis, the lines x is equals to 0 and x is equals to 1, and a curve through the points with the following coordinates. So we have the x values there, we have the y values. Now the question is, estimate the volume of the solid formed. Estimate the volume of the solid so far formed. So maybe I could give you a hint here. The volume of the solid form for this case, it's like working out the integral from 0 to 1 of pi y squared dx. So which means then in the above case, we have in the table, we have the x and y values. Then you must work out that using the above table. Then take h to be maybe, for this case, the h is 0.25. Then use Simpson's 1/3 rule. I expect you to get like 0.2.8192 cubic units.
Excuse me.
Yes.
Okay. How do we know which formula to use?
You will be asked, but this one is a bit open. You'll be required to either work it out using the new Simpson's third rule or 1/8 rule, or whichever that you will be asked to use. Any other question?
Excuse me, sir.
Yes.
Can you please move to the previous slide?
Previous slide. You mean that one? Yes?
Yes, yes.
Okay.
Oh, it's okay, it's okay.
Is that okay?
Yeah, it's okay.
Okay.
So let's have a look at another question there. The last one now. Slide. Is various over time. Of the slider, when t is equals to 0.3 seconds. So we have t in the x 0, 0.1, 0.2, 0.6. And 0.24. So we have, you should know the rate of change of displacement with respect to time gives the velocity. So you are going to integrate now between 0 and 0.6. that. Now, in this case, this is an open-ended question. You are not told which formula to use. You can decide to use Simpson's 1/3 rule, 3/8 rule, Bool's. Use any one of those to work out that. So I think I will have to stop at that point. In our next class, I would like us to have a look at we have a look at what is happening. Are you guys there? Yes? Are you there or you're gone?
We're here.
So in our next class, I'd like us to look at briefly on the numerical solutions of ordinary differential equations.
Excuse me, sir.
Yes?
I had a question. For example, the first example we did on the one we were to work out using Simpson's third rule and the 3/8 rule, the answers are different. Does it mean that each rule has varying degrees of accuracy?
Perfect. As I was moving along, depending on the n value, when we increased n, the formula became more accurate. Because if you compare the trapezoidal rule and the Bool's rule, for example, you will notice that for the Bool's rule, it will be more accurate, especially if you knew the analytical solution of the given integral. So as the value of n increases, the rate of accuracy does increase. They will not be the same, because if they were the same, then we cannot be talking about, we could not be varying the value of n.
Then now I had another question. Does it mean that it's the degree of accuracy that will always guide us on which method to use, or are there other factors that go into determining the method to use, as in practically speaking?
One thing that you must know, again, there are many formulae that you can use, and we can go, like for the value of n, we can go up to 5 or more. But for this case, then we went up to n when n is equals to 4. Depending on the question that you have been asked. Because you can be given a question, you're supposed to compare two formulas. You calculate the error, you know the analytical solution, then you work out the error depending on the formula that you have employed. So it's not always that you'll just be given an open-ended question where you decide on which formula to use. In most cases, you will be directed on which formula to apply. Any other questions again?
Yes, in the fourth problem, isn't that meant to be a derivative, not an integral? The last problem you've shown us.
In a question.
Yes, yes, sir. Yes.
So far, we know how to solve ordinary differential equations, the methods that we can use to solve the differential equations. But there are situations where you will get an ordinary differential equation which you cannot be able to solve using the analytical methods. So we're talking about the dy dx, which we can call that function of xy. And of course, we have the boundary conditions as in what we have there. So you will have to rewrite the first order, say ordinary differential equation in this form. And then once you write it in that form, you will then employ some specific formulae, which you will then use to work out the value or the numerical value of the given ordinary differential equation. So again, we are going to come up with a scheme on how we will work out that. Maybe during your free time, you can look at the following formulae, what we call the Euler's method. Then we have the Runge-Kutta of second order. And then we will we'll look at the Helms. And if we get time, then Helms method. This is the same. This is sometimes called the Helms method. That's the one. Then now the Runge-Kutta method of fourth order. So you can have a look at those three, then we can discuss that next week. So when are we supposed to do the cut now? When are we supposed to do the cut? I want us to agree today. Are you guys there?
Yes, Thursday afternoon.
Yes, we are here.
When do you want us to do the cut?
Next Thursday afternoon.
On Thursday. That will be what date?
6th of May.
Run away.
Now, sixth. No, why can't we do it on Wednesday?
How long is the cut supposed to be?
Because supposed to be 2 hours.
Oh, the issue is that Wednesday we aren't. We don't have the extra hour from 9 to 10.
There's no problem. You can have it from 7 to 9. So the reason as to why I'm saying we have it on Wednesday is because we have the class for Thursday, because we have like 1.5 chapters to wind up the syllabus. If I can have Thursday for the class, we realized we didn't have a class last week. If we can have a class for Thursday, then we have the cut on Wednesday, 5th, from 7 to 9. Is that okay?
No. 7 to 9 is not okay.
Yes.
7 to 9 is quite in order because after all, you are doing the cut from home. You are not coming to college.
7 to 9 is not okay because some people have to access cybers for them to be able to access computers.
So there is no email from 7 o'clock in the morning.
Sorry? Sorry, sir, I didn't get your question.
See, what are you saying? You access what?
I have students
I'm asking,
I'm saying.
What is the problem of you guys having the cut? Yes.
I have students from my class who attend class through cybers. But 7 a.m. no cyber is open. That means that they'll not be able to start the cut on time with the others who are taking them from home. Because most businesses open at about 8.
So we have it on Thursday from then from 2 to 3, 2 to 4. Okay.
And then we can have the class on Wednesday.
On?
We have the class on Wednesday morning.
Fine.
Okay.
Oh. These things leave them like this because there's something I have to do. Okay?